So next we have Tom Shannon with some props. We got to make sure we pass those around. This is very cool, and over to you.
Thanks. All right. Like I said, I'm Tom Shannon. I'm thankful for all of you for coming today to listen to my senior capstone project, which is on a specific topology optimization method for generative design. I'll get into what that means later because it's a bunch of fancy words, but basically how we start with this simple question. Oh. Sure.
Worked a second ago.
Yeah, a second ago.
I'll just hit the keyboard.
Yeah. All right, there you go. Check. Okay. All right. So the way we have designed things for decades has been relatively the same. We come up with an idea, and then we come up with a model. Generally, this is modeled through a CAD software program, such as Autodesk or SolidWorks. And then with that model, we usually simulate or test it. So this is just to validate if our part meets the constraints that we are designing for. And typically, that's not the case, and we have to go back and redesign it. So we draw up a new model, we simulate and test until we're happy with something that we're comfortable with. And then, and then once we're comfortable with it, we can manufacture it. And this is kind of an outdated process, especially with a lot of the new manufacturing techniques that are coming up in recent years, such as 3D printing. And with these new manufacturing techniques, we should also have new design methods. Whoa, whoa. All right, so how can we use software to help us aid in the design process? Can it ultimately be as creative as humans? Can we use this to make designs for very specific scenarios? Can these designs become lighter, cheaper to manufacture, and ultimately retain the same structural rigidity of a normal part? Cool. So that's what kind of my senior capstone project looks at, and I also am looking at how can I make a part that meets a certain set of constraints to make it the most economical part that we can look at. So we do this through something that's known as topology optimization. And through this presentation, I hope to inspire upon you like a new era of design, which is going to be coming in the next decade, which is kind of cool. Yeah. So what is topology optimization? Topology optimization is a kind of an optimization process that allows you to generate or create a part based on very initial constraints. We use these constraints to iteratively find the most optimal solution to a design pattern. And using this, we can use software to ultimately find the perfect part. So what we can do is basically say, computer, make me this perfect part that fits in this specific amount of volume and can hold this amount of mass. To contextualize this, I can give you a real-world example. So this is a moon lander frame created by Autodesk software. This was built out of the initiative to find the most economical parts for the aerospace industry. So this was specifically for a NASA lunar mission. They took old previous lunar data mission from previous moon landers and used that to drive the design, which is kind of here. So you can notice that this design has all these organic looking holes that ultimately help reduce the mass by about 30% of volume fraction. By making this 30% lighter, we ultimately save nearly $600,000 because it takes about $5,000 to send up a pound up into space. So this is really cool stuff. And basically we can use anything to optimize, like data such as force data, to optimize designs. And there's very particular and different methods that we can use to accomplish this. So finding the best method is important in order to finding new mass-saving reductions. So how does it work? Topology optimization, like I said, is very initial oriented. So you have to define very like loads and constraints. So let's say if we wanted to design something what is known as a cantilever beam in a physics scenario, we can define a system that's composed of these cubes. And these cubes ultimately have 8 nodes and 6 faces. So these just represent a small volumetric volume of the entire design. And when we place certain constraints, so we put this initial system attached to a wall on the back end, and we also attached some surface loads in a uniform fashion at the end of this cantilever beam. By doing this, when we apply a surface load, we ultimately cause strain and stress in the system, which deforms these nodes, these microscopic nodes here. And what we want to do is minimize these nodal deformations in the system. Topology optimization also conforms to a specific target volume. So from that initial design of a grid, we want to say, I want to reduce 85% of that material from that grid. And then basically it takes finite element analysis data, which is the stress and strain, the amount of deformations in the system, and tries to minimize the amount of deformations in the system in order to come to an optimal solution. So what I did for my senior capstone was implement a very specific topology optimization method known as the bidirectional evolutionary structure optimization. It's a big mess of words there, but basically what it means is it can subtract and add material. Other topology optimization methods are generally just purely reductive. So the advantage of using this is to add material where it may be prematurely subtracted. There's some mathematical theories that allow for stronger structures if you can add material later in the evolution process. So here is an animation of that cantilever beam that we discussed. So here you can see that slowly carving out material here. And it kind of creates these organic looking structures or holes in the middle, kind of like what you saw in the Autodesk design for the thing. And it's kind of hard to tell that it's adding material, but it adds a few cubes at the end, more notably there. But what's cool about this is it subtracted 85% of the total volume fraction of the surface, but still retains some structural rigidity. So if you pass those around, you can kind of see those visualizations of those as a 3D printed part. So here are the final designs. What we see here is that you also see the organic structures again, the holes. But you also see that there's remnants of human design. You can kind of see that this view looks like an I-beam structure, which is kind of cool to see human design being showing up in these optimization problems. So these structures are also ultimately kind of ugly with these rigid cubes. This was mainly done just to make the mathematics easier and to actually speed up a little bit on these optimization problems, because these optimization problems take a very long time. This took nearly 12 hours to compute. So in order to get around the rigid surface of these cubes, we can apply what is known as a Poisson surface reconstruction. It basically just allows you to smooth over the surfaces of these rough cubes. And what it does is basically it creates a point cloud of the structure and uses a mathematical solution to interpolate the surface of the material. And by doing that, we get structures that look a little more resemblant to what we might see in the real world, more smooth, what we can actually use to manufacture in 3D print, as denoted by those 3D printed structures that you've been passing around. So the really cool thing about this is it's all generated by software. There's no human design, and it looks nothing like what a human could have done. And it ultimately performs pretty well. When I put this into Autodesk to do static load analysis, it actually said, this part seems to be very over-engineered. So I thought it was pretty cool to see that. So if I had more time, there's some things that I would like to do to extend this. First of all, I would like to add a better user interface to allow people to define systems and loads more easily. As of now, it seems that the coordinate system that I had generated is very difficult to set loads and stuff. So I would include that in my future work. I would also include a distributed workload system that allowed you to distribute some of the simulation work across multiple machines to make it faster and also do higher resolution simulations. As of now, this is pretty high resolution for right now. This is like 9,600 elements, which took 12 hours, but some of the more higher end topology optimization methods can go up to 100,000 elements. So for the future, I would do something like that. And then I would also like to apply machine learning to this. Instead of having it based off topology optimization, finite element analysis, it would actually just generate it from past designs. So it'd be cool to see if artificial intelligence could come out with similar designs to that. Reflecting back on my senior capstone, it all kind of sparked from an interview rejection from Autodesk. It is actually this same guy that I was talking about earlier who interviewed me for this specific project, who said, although I really like your experience, because I have had a lot of experience with the space science projects here at Carthage, which I'm very thankful for, but you don't have the computational geometry experience that we were looking for. And I was really bummed about this, and it kind of hit me hard, so I wanted to do a project where I could prove to myself that I actually could do something as complex as this. And I did it, so I feel like I'm a lot better programmer because of this, and I'm going to be taking this into my next job as a software developer at ThoughtWorks. And then lastly, I'd like to acknowledge a few professors, because this capstone was not a solitary process. Professor Kowalowitz and Professor Bill Schrader for keeping me on track of my development during my senior seminar. And then Professor Brant Carlson for helping me with the computational physics aspects. That's it.
Said it took about 12 hours to compute that last design that you were showing?
Yeah.
Was that all computed on your CPU?
Actually, it was provided. It was just on the CPU. I would have liked to extend this to the GPU as well, but yeah, I'm very thankful for Professor Perry Kowalowitz for allowing me to use one of his bigger, beefier computers, because my laptop isn't very fast. Yeah.
So is this method more about like maximizing the weight, or like maximizing the amount of weight you can cut from a part?
Yeah. So typically, you can like say you want to take out 35% or something, and you can look at the finite element analysis to see if that part is good enough for your needs, because sometimes your part is just too massive and you don't need that much mass. So
like what you were saying earlier is when you put it into Autodesk, it said that it was sort of over-engineered.
Yeah.
Is there another way that they can use this where you set like parameters of how strong you want it to be? That way it's sort of like min-maxing structural integrity versus cost of your element?
Yeah, that's definitely a possibility.
Any questions? Tom, if this is the way you take rejection, then I say with utter contempt, you can't cure cancer.
Thanks.
Okay, folks, we have a break now, and we'll resume one floor up. And that resolution will be at 6 p.m.
machine.
It is, well, you know, that's quite a while from now. We are ahead of time. So if it's okay with you, why don't we resume, let's say, 5:45 instead of 6?
Margaret, do you have anyone coming at 6?
No, I'll do it.
Okay.